Hi all. So we are in lecture 9 talking about section 4.1, rates of change. And if you watch the first video, I took you through kind of an explanation of the concepts of rates of change and leading into the idea of derivatives, which are instantaneous rate of change. What I want to do now is I want to kind of expedite the process. So we went through a couple examples where we said, here's a function. In fact, there's one right up here. Now this one's not filled in, but yours should be at this point. We had a function 1 over 2x, and I asked you, oh, find the derivative at 1 and find the derivative at 2. And we had to use a limit in each case to find the separate value, the limit at that separate value. Okay, so what happens if how can I expedite that process? How can I make it faster? Or what happens if I don't want to know what the derivative is at a point? I want to know what the derivative is in general. So what we want to do is we want to go back and look at how we found that limit and see if we can generalize it. Okay, so what we did before was we said, okay, let's take that to the x squared plus 3 function, right? And we started using multiple values to find the secant lines. We looked at the slope of the secant lines, right? We had started with something like, oh, let's start with x equals 2 because we were looking for the limit at 2 and x equals 5. And you found the limit of as m equals f of 5 minus f of 2, right? We find the slope by subtracting the y values over 5 minus 2, okay? Now, what I'm going to do is instead of writing it that way, I want to write it as this. I want to think about everything from the vantage point of the 2, okay? So not two numbers, not 5 and 2, but everything from the vantage point of the 2. So that means that 5 is 2 plus some amount. Well, in this case, 5 is 2 plus 3 minus f of 2 all over. And 5, how far away is 5 from 2? 5 minus 2 is 3. So I want to think about this format. Okay. And then we simplified it and went on from there, right? And then what we said is, okay, now that we have that one, let's go and get the slope at 2 and 4, 2 points that are closer together. So in that case, we would find f of 4 minus f of 2 all over 4 minus 2. And so what we would do now in this case, what I'm going to do is I'm going to look again at everything from the vantage point of that 2. So instead of having f of 4, I want f of 2 plus 2, right? So you're kind of thinking of as what is the point of focus and then how far away am I? And then 4 minus 2 is 2. Okay. And then our next point was x equals 2 and x equals 3. So we had m equals f of 3 minus f of 2 all over 3 minus 2. And this turns out in the same kind of format to be f of 2 plus 1 minus f of 2 all over 1. Okay. And that last one we had was 2 and 2.5. And so we had the slope equals f of 2.5 minus f of 2 all over 2.5 minus 2. And so in this format, again, I'm going to write that as f of 2 plus 0.5 because that's what gets me to 2.5 minus f of 2 all over 0.5. And you may be saying, well, this seems like a really weird way to go about this. And it might be. But what I'm doing is I'm trying to generalize for the 2. So before, what we said was like, oh, let's let our 2 be the x, right? And let our x, or our a, right? And we had x was the number that was changing, right? So we had f of x minus f of a over x minus a. And we did that from the column on the left from the screen you're looking at. But what I want to do is I want to adjust that. So what I want to do is I want to think, okay, this 2 right here, I want to allow that to vary so that I don't have to pick that number right from the get-go. So we're going to let that 2 be our x. That's going to be our x. And then the number that changes as I get closer to the correct value, before was the 5, 4, 3, 2.5. Now I want that to be the other number that's changing. So I want to look at this number here. And really that's the distance from my first point to my second point. And so if we do that, we're going to let that number be our h. Okay. And if we do that, now we have an expression that's going to look like this. We have f of x for the 2 plus h for the other value that's changing, right, the yellow one, minus f of x all over, and that number that changes on the bottom is exactly the same as the h up there, so that's my h again. And what we want to do, if you notice, my h value goes from 3 to 2 to 1 to 0.5, and that's the distance between my 2 points. And we want to bring those 2 points as close as possible. So we're going to take the limit here as that h goes to 0, and this is what we're going to call f prime of x. Okay. And so that's what's going to go in my box down here is the limit definition of the derivative. So the limit definition of the derivative is exactly that, right? You're just looking at what is the slope at this line, right? What is the slope of the tangent line at that point? And we find it by using this. And so we can write that down here, f prime of x equals, and again, we're using that good notation, f prime of x equals the limit as h goes to 0, f of x plus h minus f of x all over h. Okay, and so what this does is this allows us to find this limit, right? Let our h goes to 0. That's going to give us the derivative in terms of x. And then if I have points that I want to plug in for x, we can do that. So from example 4, our last one here in the lecture, it's going to look something like this. So we're going to let our f of x be 2x minus 3, and we're going to start with that formula. So we know that f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. Okay, now the key thing here is to know what this notation means, right? And how do we apply it? So this is equal to, we keep our limits because we're going to still have x's and h's here. And now when you see the f of x plus h, that means that you're going to take the x in your function and replace it with an x plus h. So this x after the 2 will become an x plus h. Key thing here, you want to make sure that you go ahead and keep that x plus h in parentheses. So we're going to have 2 times x plus h minus 3. Okay, so that is my f of x plus h. There's only one x in the 2x minus 3. I replace that x with an x plus h. Okay, minus. Now I'm going to subtract the original function. Key thing, keep it in parentheses. So the original function is 2x minus 3. All of that gets divided by h. And from here, now we're back into our regular limits. So we're going to go ahead and simplify. We're going to distribute all the things, cancel anything, and see if we can simplify this limit. So my first strategy is going to go ahead and distribute everything. I'm going to distribute the 2 and the negative. And that's going to leave me with the following. The limit as h goes to 0, 2x plus 2h minus 3 minus 2x plus 3 all over h. Okay, now this is kind of set up in a particular way, so certain things should happen the same every time. So if you look in the numerator here, everything that does not have an h should cancel, and it does. So my 2x here cancels with my negative 2x over here. My negative 3 cancels with the positive 3, and what I'm left with here, and it's always good to rewrite this before you do anything with the h's, is 2h is the only thing left on the top, and an h is the only thing left on the bottom. And now that should always happen. So everything on top should contain an h, which means you can factor it out. So at this point, if I had more than one term on the top, I would factor the h out to the front. Then I could go ahead and cancel them before I plug anything in. And this gives me the limit as h goes to 0 of 2. Now, I lost my h's. They all canceled out. So taking the limit as h goes to 0 means you plug a 0 in for h. I don't have any. So I just stay with the same function that I have, and I get the value of 2. And what that means in this case is that the slope of the tangent line, the derivative, is always 2, no matter what the x value is. So that means that f prime of x is equal to 2. If I plug in 1, well, there's nowhere for me to plug in a 1, so I still get 2. If I plug in 2, I get 2. And if I plug in 0, I get 2. It's always 2. Why is it always 2? Well, because if we think about our graph, So our line is 2x minus 3. So intercept at -3, slope of 2. It looks like this. At any given point, we want the tangent line at that point, and the tangent line to a line is the line itself. It's kind of weird, but there's no way that I can touch the graph and kind of bounce off in a straight line unless I'm on the line. Okay, so that means that this is the tangent line. And the slope of the tangent line then is 2. And that's what represents our derivative, remember, because the derivative is the slope of the tangent line, or the instantaneous rate of change. Okay, now as these get more complicated in our guided practice, you're going to see that we're going to have x's that remain in your derivative. So you would go through and you're going to go through the same process. All the same things are going to happen. You're going to cancel out lots of things with x's that don't have h's. Then everything in your numerator will have an h in it. You can factor it out to the front and cancel it with the one in the bottom. Because if you can't cancel the one in the bottom, then you're going to end up with 0 over 0, which is an indeterminate form. So factor out that h, cancel it, and then you should have something that has x's in it, right? If you have something more complicated than 2x minus 3. And at that point, that is your derivative in general. And then if you want the derivative at various points, you could plug in the number for the x in the derivative. So remember that this notation here says that you are finding the derivative and plugging in the point 0. So f prime represents the derivative and 0 represents the point that you want the derivative at. So find the derivative in general first, then plug in your 0. Okay. So limit definition of the derivative. The limit as h goes to 0 of f of x plus h minus f of x all over h.